Hello friends, good afternoon and welcome to our EduSat network. Our today's topic of discussion is carboxylic acids, and today is part 3, and I would also like to tell you all that this is the last lecture as part of this series. So friends, please pay close attention, and also just heads up for you to know that there are more parts which you could watch on YouTube to ensure the connectivity. And friends, for this lecture we have with us in our studio Dr. K.K. Arora, Associate Professor, Department of Chemistry, Zakir Hussain, Delhi College. Sir has been teaching for more than 3 decades, and it would be very fortunate if we all can gain from his experience and expertise. So friends, with this I welcome sir. Thank you sir for coming, and sir, I request you to begin our today's lecture.
Thank you. Hello viewers. Welcome to this last session on carboxylic acids. In our previous sessions, we have discussed that what are these compounds, that is carboxylic acids, what is the structure of their functional group, how these compounds are generally obtained, and what are their common properties. Today we shall take up some substituted carboxylic acid, and our today's lecture has been planned like this, that we will discuss methods and preparation of properties of substituted carboxylic acids. And amongst these substituted carboxylic acid, we will take up halogeno-carboxylic acid, hydroxy acids, and most common acids malic acid, tartaric acid and citric acid we will discuss in slight detail. Then we shall take up some unsaturated carboxylic acids. So, we have discussed earlier that if there is some substitution in a compound, we call that as a substituted compound. So, if there is a substitution in carboxylic acids, we will call them substituted carboxylic acids. But in carboxylic acids, substitution can occur at 2 different places. One in the side chain, and second in the carboxylic group itself, where OH group gets substituted. So, we have divided these derivatives of carboxylic acid into 2 different groups arbitrarily. We call substituted carboxylic acids those acids which have substituent in the side chain, where hydrogen of the side chain has been replaced by some group like amino, hydrogen, hydroxyl, etc. And those compounds in which OH group of the carboxylic group is substituted, we call them as carboxylic acid derivatives. And we have there 4 groups of carboxylic acid derivatives. These are called acid amides, acid chlorides, esters and anhydrides. We will discuss these carboxylic acid derivatives in a separate session. But today we will discuss those carboxylic acids where substituent is present on the side chain. We will not take up amino substituted carboxylic acids, because amino acids are more related with the proteins and they are discussed there only. So, we are going to discuss halogen substituted and hydroxyl substituted carboxylic acid in our today's session. Like some examples are hydroxy substituted acid, like when this OH group is substituted here. This is the carboxyl functional group, and this H has been replaced by this OH group. Then halogen, this green color indicates halogen, some halogen has replaced one of the hydrogen, and then this is NH2 group that has replaced one hydrogen. So, these are amino substituted, halogen substituted are hydroxy substituted carboxylic acids. For their nomenclature, we have discussed earlier that any substituent in the carbon chain is there. Carboxyl carbon is given number 1, and then we continue 2, 3, 4 and so on in the IUPAC system. But when we want to name these acids according to common system, then the carbon to which carboxyl group is attached is called as alpha carbon. So, any substituent on this carbon in common system will be called as alpha substituted, and according to IUPAC system it will be carbon number 2. So, this is the one point that must be remembered, that C2 position in the IUPAC system corresponds to the alpha position in common names. We will now take up different examples for this nomenclature, because basic system of nomenclature we have already discussed in carboxylic acids. But just to revise, we will take some examples with the halogen substituent, and wherever halogen is there, if some other group comes, it will be named accordingly, such as this acid has chlorine at this carbon. So, according to common system, it is alpha chloropropionic acid, because there are 3 carbons in the chain, and according to IUPAC system, it is 2 chloropropanoic acid. Suppose instead of chlorine it is hydroxyl, then it will become 2 hydroxy propanoic acid. If it is amino, then it will be 2 amino propanoic acid, and so on. This one having substituent at the beta position, this is beta chlorobutyric acid, or according to IUPAC system it is 3 chlorobutanoic acid. Then this one having substituent at the gamma carbon is gamma chlorovaleric acid, or 4 chloropentanoic acid, because in the chain there are 5 carbons. If there are more than one substituent, as in this example, this is having one bromine here and then one chlorine here, and then there is a iso group in the end. So, according to common system, it is alpha bromo beta chloro isovaleric acid, and in IUPAC system it is 2 bromo 3 chloro 3 methyl butanoic acid. Now, as far as basic methods for the preparation of halogeno-substituted carboxylic acids are concerned, they include Hell-Vollard-Zielinski reaction. This reaction we have discussed as a property of carboxylic acid, where halogen gets substituted on the alpha carbon when a carboxylic acid containing alpha hydrogen is treated with halogen in presence of red phosphorus. If there are more than one alpha hydrogen available with excess of halogen, di or tri substitute derivatives can also be obtained. For example, this is propanoic acid. When it is treated with one equivalent of bromine, we will get 2 bromo propanoic acid. Then they can be obtained by the reaction with sulfuryl chloride, although only chlorine substituent can occur, such as this acid propanoic acid. When it is treated with sulfuryl chloride, on reaction we get 2 chloropropanoyl chloride, because the OH of the acid also gets substituted, but when it is treated with water, then that gets back into carboxyl group, and we get 2 chloropropanoic acid, or alpha chloropropionic acid. Then we can get these acids from malonic acid. Malonic acid can be alkylated. So, we start with, say, alkylated malonic acid. Some alkyl group is already substituted here. This on bromination, we can get one bromo here. These acids on heating very easily undergo decarboxylation. So, one of the carboxyl group will be lost as carbon dioxide, and we will get alpha halogenated carboxylic acid. Depending upon the R group here, we will get corresponding acid. Then we can get these halogen acids from the hydroxy acids also. The hydroxyl group of the carboxylic acid can be substituted on treatment with PCl5. So, what will happen? This OH as well as the OH of the carboxyl group both get substituted by chlorine, but this acid chloride portion is converted back into acid on treatment with water, and we get chloro substituted carboxylic acid. We may treat it with even HBr, say it is alpha hydroxy propionic acid. This on treatment with HBr gives us alpha bromo propionic acid. Then we can carry out the addition of halogen acids to unsaturated acids, where addition of HX will occur, HCl, HBr, HI can be added, and we can get correspondingly chloro, bromo or iodo substituted carboxylic acid. If we have this alpha beta unsaturated acid and we carry out the addition of HBr, now HBr will add across this pi bond. There is a possibility of formation of two products. The bromine may go to this carbon, that is the alpha carbon, or to the beta carbon. Now, if you remember the Markovnikov rule, which says that during the addition the negative part of the addendum goes to the carbon with less number of hydrogen atoms. So, according to that, the bromine from the HBr should go to alpha carbon, and we should get alpha bromo substituted acid. but actually we get here beta bromo substituted acid. So, we will discuss the reason for this little later. This addition may be carried out even to unsaturated aldehydes also, which may be later oxidized into carboxylic acids. Like this is a 3 carbon aldehyde and addition may occur across this double bond. Suppose we are carrying out the addition of HCl. Again the negative part is going to this carbon, that is a beta carbon, and not to the alpha carbon. As I told you, we will discuss the reason little later. Then these acids can be obtained by the oxidation of halohydrins also. Halohydrins means compound which are alcohols and having some halogen substituted to it. These on oxidation, if the primary alcoholic group is there, it will be oxidized into carboxylic acids. We can get iodo-substituted acids specifically by the replacement of chlorine or bromine in chloro or bromo carboxylic acids, and that reaction is called Finkelstein reaction. In this, say if we have this bromo substituted acid, it is treated with potassium iodide in acetone or methanol, then this bromine gets substituted by iodine and we get corresponding iodo substituted acid. Say if you are starting with alpha bromo propionic acid, we are getting alpha iodo propionic acid. Then using the Hunts-Dicker reaction, you must have studied this reaction in the preparation of alkyl halides, particularly alkyl bromides from carboxylic acids, where carboxylic acids lose a molecule of carbon dioxide, that is there is a degradation in the chain by one carbon and halogen occupies that place. Here we use it on monoesters of dicarboxylic acids. If we have a dicarboxylic acid and this is a monoester, on this side a free carboxyl is there, we prepare its silver salt on treatment with silver nitrate in alkaline medium or maybe with silver hydroxide, and then this silver salt is treated with bromine. Now what will happen? On this carbon dioxide is lost and bromine gets attached here. So we get a bromo substituted ester which can be hydrolyzed later to give us bromo substituted carboxylic acid. Let us take an example. This is a 1, 2, 3, 4, 5 carbon acid, glutaric acid, and its ethyl ester on one of the carboxyl group. So we call it as ethyl hydrogen glutarate. This on treatment with moist silver oxide forms the silver salt here. Then it is treated with bromine, then carbon dioxide is lost from here and we get CH2Br, and then this ester is hydrolyzed and in the end we get this bromo substituted carboxylic acid. Remember, we started with a 5 carbon carboxylic acid. In the end we will get a 4 carbon in the chain because one carboxyl group is lost as carbon dioxide during this reaction. Now briefly let us take up the properties. These are carboxylic acids and they show all the reaction of carboxyl group that we have discussed earlier, means they react with bases like sodium bicarbonate to form sodium salt with the release of carbon dioxide. They react with alcohols to form esters. They will react with acid chlorides or PCl5 etc. to form acid chlorides, and they will react with substituted acid chloride also to give corresponding anhydrides when this acid part is taken as sodium salts. These are the basic reaction which we have studied for simple carboxylic acids. Now only difference is that in all these cases we have taken a chlorine substituted carboxylic acid. Similarly, it may be bromine or iodine. All these reactions are shown. These reactions are not different. Now as far as the acidic strength of halogeno-acids is concerned, we have already discussed the acidic nature and what happens when a group is introduced on carboxylic acids on the acidic strength. It is just to revise briefly that chlorine is an electron withdrawing group and delocalizes the negative charge on the carboxylic acid, and hence it increases the acid strength, and more is the number of chlorine or other halogens, stronger will be the acid. This is the example. This is acetic acid. These are pKa values given. pKa for acetic acid is 4.7, and if we have chloroacetic acid, pKa is 2.8, if it is dichloroacetic acid, pKa becomes 1.3, and for trichloroacetic acid it becomes 0.9. You know that higher the pKa value means weaker the acid. So, strongest acid amongst these is trichloroacetic acid. Then inductive effect also plays a role because it is acting through the sigma bonds, and as the distance of the electron withdrawing group increases, acidity decreases. This is a 4 carbon acid, butanoic acid, with a pKa value of 4.9. When it is alpha chlorobutyric acid or 2 chlorobutanoic acid, that is chlorine is present at the alpha carbon, the pK is 2.8. But when it is present at the beta carbon, it is 3 chlorobutanoic acid, pK is 4.1, and when it is 4 chloro, then pK becomes 4.5. So, as chlorine is moving away from the carboxyl, we find that pK value is increasing. But even if chlorine is present at carbon number 4, this is stronger than simple butanoic acid. When this halogen is fluorine, chlorine, bromine or iodine, their electronegativity decreases, means their electron withdrawing power decreases. Hence, the fluorine substituted acid should be the strongest acid, and when it is iodine, it should be weakest acid, and we find that their pK value also decrease in the way when it is fluorine, pK is 2.6, with chlorine 2.8, with bromine 2.9, and with iodine it is 3.2. Then reactions due to this halogen atom. The alpha halogen is more reactive when present at the alpha position and can be easily substituted by various nucleophiles. You remember that most common properties of alkyl halides are nucleophilic substitution reaction. These reactions are there that carbon halogen bond is a polar bond and a nucleophile comes and attacks this carbon, halogen gets displaced. These are classified as nucleophilic substitution reaction. Now, in this carbon, one carboxyl group is also there, which is an electron withdrawing group. So, now what happens? This carbon becomes even more electron deficient. So, nucleophile can easily attack and this substitution reaction becomes easy. So, various nucleophiles which you have studied in alkyl halides can be used to displace halogen in alpha halocarboxylic acids also. Like if it is chloroacetic acid, on treatment with moist silver hydroxide can be replaced by OH. On treatment with silver nitrate, this is displaced by NO2. On treatment with potassium iodide, it is iodine taking the place of chlorine. On treatment with KCN, cyano group gets introduced, or on treatment ammonia, we get amine group coming in the place of chlorine, but since ammonia is a base, it forms the ammonium salts also, which get hydrolyzed to get the corresponding amino acids. There is a specific reaction with alkali for differently substituted halogen acids. That is, if halogen group is present at the alpha position, beta position or gamma position, different products are obtained on treatment with alkali. When it is alpha halogeno-acid, like this. Now, what happens? This on treatment with alkali, simply halogen gets displaced by OH group. It may be sodium hydroxide or sodium carbonate or silver oxide, like all these bases can replace this halogen by OH group, and we get corresponding hydroxy acids. If it is a beta halogen substituted acid, this on treatment with alkali, instead of undergoing substitution, undergoes elimination reaction taking a hydrogen from the alpha carbon, and we get alpha beta unsaturated carboxylic acids. If it is at gamma position, then a reaction occurs with the carboxyl group and the chlorine, which involves ultimate loss of HCl, and a cyclic ester is formed. The cyclic esters are called lactones. What happens in presence of this alkali? This carboxyl group gets ionized and O minus end of the carboxyl group acts as a nucleophile, and it is a suitably placed group. Now this nucleophile attacks this carbon and Cl gets displaced and we get cyclic esters. Since this is at the gamma position to this carboxyl where the ester has been formed, so these are called gamma lactones. Similarly, if it is a delta substituted chloroderivative, we will get a delta lactone. Next we take up hydroxy acids. As I said earlier that when any of the hydrogen is substituted by hydroxyl group, we call them as hydroxy acids. If this hydroxyl group is present at the alpha carbon, then these are called as alpha hydroxy acids. If it is at a beta carbon of the chain, we call them as a beta hydroxy acid. If it is a gamma carbon, we call them as gamma hydroxy acid, and so on. Alpha hydroxy acids are symbolized as AHAs, and they are more important as far as our routine life is concerned. This is general representation for any alpha hydroxy acid. These alpha hydroxy acids occur naturally in many fruits, milk and sugar cane, and they are used in many skin care products, medicines and soft drinks. These days it has been observed that simply substituted alpha hydroxy carboxylic acids play an important role in various skin care products where anti-aging effect is observed for these compounds. And some common hydroxy acids are like lactic acid, this is an alpha hydroxy acid; mandelic acid, this is an alpha hydroxy aromatic acid, it is having an aromatic substituent also; and this is salicylic acid. It is with respect to this carboxyl is a beta hydroxy acid, but it is generally studied with the phenolic acids, and there are different derivatives of salicylic acid like aspirin or methyl salicylate, or even simple salicylic acid itself they find use in medicines. Then some other common hydroxy acids which are important part of our food items, these are malic acid. Malic acid is a dicarboxylic acid with one hydroxyl substituent. Then tartaric acid. Tartaric acid is again a dicarboxylic acid with two hydroxyl groups as substituent. And citric acid, it is a tricarboxylic acid with one hydroxyl group present in it. So we will discuss these three acids in slight detail because they are the constituent of many food items. General methods for the preparation of hydroxy acids include by the hydrolysis of alpha haloacids. We have discussed earlier that halo group present at the alpha position can easily be substituted by hydroxyl group on treatment with potassium carbonate or sodium hydroxide or silver oxide, and we get corresponding hydroxy acid. Then there is another example with silver hydroxide. Then by the action of nitrous acid on alpha amino acids. As I told you, alpha amino acid constitutes proteins. So they are obtained from proteins also, and they are synthesized in the laboratories also. These alpha amino acids can be converted into alpha hydroxy acids on treatment with nitrous acid, where diazotization of this NH2 occurs, but these diazonium salts are unstable and it is replaced by OH group. So we get corresponding hydroxy acids. Then by the control oxidation of glycols, means if a compound has got more than one hydroxyl groups, then the primary hydroxyl part can be oxidized, like in this case it is 1,2-propane diol. This primary hydroxyl group gets oxidized by dilute nitric acid and we get lactic acid in this case. This alpha hydroxy acids can also be obtained by the hydrolysis of cyanohydrins, which are obtained by the addition of HCN to aldehydes or ketones. This is an aldehyde. If HCN is added, CN will go to this carbon and H goes to oxygen. We get this compound which has OH group as well as CN group. We call them as cyanohydrins. And then cyano group can be hydrolyzed into corresponding carboxylic acid group, and we will get alpha hydroxy acid in this case. Like acetaldehyde on addition of HCN followed by this hydrolysis gives us lactic acid. Then beta hydroxy acids. Beta hydroxy acids are obtained by one very important reaction which is called Reformatsky reaction. Reformatsky reaction involves the treatment of alpha bromo esters with zinc. This is methyl acetate having bromine at this substance, so it is methyl bromoacetate. This one treatment with zinc forms here a ZnBr. Like Grignard reagents are formed by reaction of alkyl halide with magnesium, here it is zinc. And then these compounds, these organometallic compounds, when on treated with some aldehyde, they undergo the nucleophilic addition. And this part, this carbon goes to carbon and ZnBr goes to this oxygen, and we get this compound, and then this gets hydrolyzed ultimately to give corresponding OH. So, we have now obtained an hydroxy ester and it can be hydrolyzed to give us an hydroxy acid. In this case, since bromine was originally present at the alpha carbon and it is this alpha carbon which has attacked to the carbon of aldehyde or ketone, and here it is this carbon which ultimately gets the OH group, so it is the beta carbon and we always get beta hydroxy acids in this reaction. So, this Reformatsky reaction is especially used for the synthesis of beta hydroxy acids. Then we can get these beta hydroxy acids by the addition of water to alpha beta unsaturated acids also, and this addition is same electrophilic addition that I discussed before for the addition of HBr, and here also this negative part OH is going at the beta position. Then keto acids and keto esters can be reduced, this CO can be reduced to CHOH, and if it is ester, that will be ultimately hydrolyzed. So, what happens wherever this CO group is there in the chain, it will be becoming CHOH. So, we will get corresponding hydroxy acid from the corresponding keto acid. Then action of heat on hydroxy acid. This is one of the again very important reaction for the hydroxy acids, that alpha hydroxy acids, beta hydroxy acids, gamma hydroxy acids, they give different products on heating. So, we are discussing this reaction mainly for this. Alpha hydroxy acids such as lactic acid as an example, they form lactides via intermolecular esterification. What happens in this reaction? Two molecules of the alpha hydroxy acids, they react, and hydroxyl of one forms the ester with carboxyl of the second, and hydroxyl of the second combines with the carboxyl of first to form a diester like this. This is lactic acid. This is the COH of the first say lactic acid molecule, OH from here, and this is the second lactic acid molecule, this H from the hydroxyl, they eliminate water, and OH of this carboxyl and H of this alcohol, they eliminate water. So, we get a diester. These diesters are named as lactides, and for this the compound that is obtained from lactic acid, we name it as 3,6-dimethyl 1,4-dioxane 2,5-dione. Beta hydroxy acids on heating eliminate water molecule by taking hydrogen from the alpha carbon and giving us alpha beta unsaturated carboxylic acids. Then gamma hydroxy acids and delta hydroxy acids, both they form an intramolecular ester, that is hydroxyl of the chain and carboxyl of the same molecule, they eliminate a water molecule forming a cyclic ester which are called lactones. When hydroxyl group is at a gamma position, we get this ester which is called gamma lactone, and if we name completely, there are 4 carbons in the chain, so we call it as a gamma butyrolactone. And if it is a delta hydroxy acid, we will get corresponding delta valiroketone, delta valirolactone. Lactone is the name given to cyclic esters. We will take up briefly now the specific examples like malic acid. Malic acid occurs in sour apples, grapes and most of the berry fruits. These all contain malic acid. Malic acid can be prepared from the juice of berry fruits. The juice from the berry fruits which contains malic acid is treated with calcium hydroxide, that is lime, and is precipitated as calcium malate. Then this calcium malate is filtered and is treated with calculated amount of sulfuric acid, and we get malic acid. It can also be obtained by the hydration of malic acid or fumaric acid. We have discussed earlier that malic or fumaric acid are the geometrical isomers. These are the acid with carbon-carbon double bond here. The cis isomer is called malic acid and trans isomer is fumaric acid. When a water molecule is added across this double bond in presence of acid, we will get malic acid. Then we can get them by the partial reduction of tartaric acid. As I told you earlier, tartaric acid contains 2 hydroxyl groups. So, one of the hydroxyl is reduced on treatment with HI and we get malic acid. We can get this malic acid from bromosuccinic acid, CH2CH2, COH, COH, this is succinic acid, and this on Hell-Vollard-Zielinski reaction gives us bromosuccinic acid, which can be hydrolyzed very easily with moist silver hydroxide to give us malic acid. Then as far as some properties are concerned, malic acid, it behaves as alpha hydroxy with respect to one carboxyl group and beta hydroxy with respect to the other carboxyl group. So, we have seen earlier that these alpha and beta hydroxy acids on heating give different products, but when this malic acid is heated, it behaves more like a beta hydroxy acid and a molecule of water is eliminated. When a water molecule is eliminated from this carbon and this hydroxyl group, we can get again cis and trans isomers. So, if we get the cis isomer, that is malic acid, it will also eliminate a water molecule from here and it will form malic anhydride. But we get a trans isomer, then 2 carboxyls are away and we will get fumaric acid. So, malic acid on heating gives us a mixture of fumaric acid and malic anhydride. Then it can be reduced with HI. This hydroxyl gets reduced and we will get succinic acid. This on oxidation, this CHOH part gets oxidized into CO, we call it as oxyl acetic acid. This is now CO with carbon having alpha hydrogen along with it, it can undergo ketone tautomerism. This is the keto form and this is the enol form. Then uses of malic acid. It is used as a food acidulant and as a remedy for sore throat. Then next we take up tartaric acid. Tartaric acid occurs in grapes as a potassium salt. All variety of grapes contain tartaric acid in them. Then it occurs in plenty in tamarind. There are many other fruits also which contain tartaric acid. These two are the rich sources. This tartaric acid is prepared from argol. Now, what is argol? Argol is a crude potassium acid tartrate which separates during fermentation of grapes. When grape wine is obtained and these grapes are fermented, then this potassium acid tartrate gets precipitated there. Then this potassium acid tartrate means one of the carboxyl is as potassium salt, other is as carboxyl group, it is treated with calcium hydroxide. What happens? A disproportionation occurs. We get a dipotassium tartrate as well as the calcium salt of this tartrate, that is calcium tartrate. Calcium tartrate is insoluble, gets precipitated, and dipotassium tartrate remains soluble. Then it is further treated with calcium hydroxide and calcium chloride here, and this potassium tartrate gets also precipitated as calcium tartrate, which is insoluble. Now it is filtered, and this filtered solid calcium tartrate is treated with calculated amount of sulfuric acid, which converts it into tartaric acid. So, this is one way of getting tartaric acid. Then tartaric acid can be obtained from succinic acid also. It is subjected to Hell-Vollard-Zielinski reaction with 2 moles of bromine. We get a dibromosuccinic acid which on hydrolysis will give tartaric acid. It can be obtained from glyoxal also. Glyoxal is this dialdehyde. When addition of HCN is carried out, it occurs at both the aldehyde group, we get this dicyanohydrin, this is hydrolyzed and we get this dihydroxy and dicarboxylic acid, that is tartaric acid. It can be obtained from glyceraldehyde by Kiliani-Fischer synthesis. Kiliani-Fischer synthesis is the reaction in which chain length is increased by 1 carbon on aldehydes. So, glyceraldehyde is a 3 carbon aldehyde with 2 hydroxyl groups. Here chain length is increased, this is treated with HCN, we get cyanohydrin, then it is hydrolyzed and on acidification we get corresponding carboxylic acid. Now, these two are secondary hydroxyl group, this is a primary alcoholic group, and on mild oxidation this can be oxidized and we ultimately get tartaric acid in this. Then this tartaric acid can be obtained by the oxidation of fumaric acid or malic acid. As I told you before that fumaric acid and malic acids are geometrical isomers, fumaric is trans isomer, malic is cis isomer. When they are oxidized by KMnO4, then 2 hydroxyl group add across this carbon-carbon double bond from the same side. So, fumaric acid gives us 2 isomers which are DL mixture, whereas malic acid gives us the meso isomer of tartaric acid. Tartaric acid has got 2 carboxyl groups, so it can give 2 series of salts. It is potassium hydrogen tartrate or dipotassium tartrate, and it also forms the mixed salts like sodium potassium tartrate, which is known as Rochelle salt. Then it can be potassium antimonyl tartrate, which is used in medicines. They react with ammonical silver nitrate, and ammonical silver nitrate is Tollens reagent. Tollens reagent gets converted into silver, and this tartaric acid is also used in silvering of mirrors, because this reaction is bit slow here and smooth layer of silver is obtained on the glass surface. The tartaric acid itself gets converted into tartonic acid on treatment with ammonical silver nitrate. This tartaric acid can also be oxidized by Fenton's reagent. Fenton's reagent is ferric ions in presence of hydrogen peroxide. Here also a mild oxidation occurs and this carbon-carbon bond gets converted into carbon-carbon double bond, and we get hydroxy malic acid in this case. Then tartaric acid can be reduced also. This hydroxyl group can be reduced on treatment with HI. In the first step we may get malic acid, which on further reduction will give us succinic acid. Then this can react with HBr, where hydroxyl group can be replaced by Br and we can get dibromo succinic acid. Then action of heat. As I told you before, one of the important reaction for hydroxy acid is their action of heat. They behave in different way. When this tartaric acid is heated at lower temperature, it simply forms an anhydride here, we call it as tartaric anhydride. But when it is heated to high temperature, one of the carboxyl group undergoes a decarboxylation and we end up with pyruvic acid, CH3CO, COH. When this tartaric acid is heated with potassium hydrogen sulfate, in the first step a dehydration occurs. We get here the double bond and hydroxyl. This is the enol form, it may exist as a keto-enol tautomer, this undergoes in the keto form, and then it undergoes decarboxylation because carboxyl group is next to the carbonyl. So, this reaction occurs one after the other and ultimately we get pyruvic acid. So, tartaric acid on heating with potassium hydrogen sulfate also yields pyruvic acid. Then uses of tartaric acid. It is used as acidulant in soft drink. Most of the soft drink that we contain, they contain tartaric acid. It is used as effervescence producing tablets. You must have seen aspirin tablet which produces effervescence when dissolved in water. It is due to the presence of tartaric acid and sodium bicarbonate into it. Then it is used as a Rochelle salt, that is sodium potassium tartrate. It is used as laxative and also used in Felling solution. Then tartarimatic, the potassium antimonyl tartrate. it is used as medicine as an eliminant of poisons. If anybody has taken the poison, then this tartar emetic is given, which causes vomiting and emission of poison from the body. Then potassium acid tartrate is called as a cream of tartar, which is used in baking powder, and tartaric acid is also used as mordant in dyeing. Then a third important hydroxy acid we discussed briefly is citric acid. Citric acid has got 3 carboxyl groups and 1 hydroxyl group in it. It is found in all variety of citrus fruits. All the citrus fruits, they contain citric acid in them. That is why they have been named as citrus fruits. Then basic method for the preparation of citric acid includes the fermentation of molasses. Molasses is the waste of sugar industry. After the crystallization of sugar, we get dark viscous liquid that still contains lot of sucrose in it, and is called molasses. So it is fermented and we get citric acid. It can be obtained from glycerol also. Glycerol, you know, is a byproduct of soap industry. This on treatment with HCl gives us a dichloro derivative with the primary hydroxyl groups are replaced by Cl. Then it is oxidized by mild reagent, and this secondary alcohol group gets oxidized into corresponding ketone. Then to this ketone, addition of HCN is carried out and we get cyanohydrin on this carbon, a cyano and OH. Then it is treated with KCN, both the Cl groups are also replaced by Cn, and now we get a tricyano derivative, and this is hydrolyzed. So these tricyano groups on hydrolysis give tricarboxyl groups and we get citric acid in this way. This is one of the important methods which is used for the commercial production of citric acid starting from glycerol. Glycerol can be obtained using Reformatsky reaction also. I discussed just before that Reformatsky reaction involves the treatment of alpha bromoesters with aldehydes or ketones in presence of zinc. So here that reaction is used. We take ethyl bromoacetate and oxyl acetic ester. This is this carbonyl group on which the addition will occur in presence of zinc. First this ZnBr is formed and then it adds on this carbonyl and we get this intermediate. This is hydrolyzed and we get citric acid. Citric acid has got 3 carboxylic acids, so it gives 3 series of salts. These may be monopotassium citrate, a dipotassium citrate or tripotassium citrate, or similarly with other metal ions we can have mono, di or tri metal salts of the citric acid. There is one hydroxyl group, it can be acetylated on treatment with acetic anhydride, we get corresponding acetyl substituted citric acid. Then these citric acid can be reduced also. This OH group is reduced on treatment with HI and we get tricarboxylic acid, where this OH is replaced by H. Action of sulfuric acid. Citric acid on treatment with fuming sulfuric acid, that is oleum, undergoes a reaction on this carbon where this is converted into C double bond O. Then it can form complexes also with different metal ions, and metal ion with copper is used in the Benedict solution. Benedict solution contains complex of copper with citric acid in action of heat. Citric acid on heating up to a temperature of 150 degree simply loses a water molecule like this and we get an acid called aconitic acid. But when it is heated to high temperature, two series of decomposition may start. One, a reaction occurs across this carbon and we get acetone dicarboxylic acid. From here 1 molecule of water and 1 molecule of carbon monoxide are lost. We get this acetone dicarboxylic acid, which on heating undergoes decarboxylation on one side to give us acetoacetic acid, and the second carboxyl group can also be decarboxylated, and ultimately we get acetone. So, one series of decomposition leads to acetone. Then another series also starts, and here a loss of water occurs initially to give aconitic acid. Then this aconitic acid further will undergo decarboxylation on the carboxyl group, which is attached to carbon-carbon double bond or carbon-carbon single bond, to give again two different dicarboxylic acids. These are itaconic acid and citraconic acid or mesoconic acid, and these dicarboxylic acid on further heating lose a water molecule to give corresponding anhydride. These are itaconic anhydride and this is citraconic anhydride. These compounds here, the citraconic acid or mesoconic acids, they are actually geometrical isomers, but once they form the anhydride, that will be formed only from the cis isomer and not from the trans. So, we get only citraconic anhydride. Then uses of citric acid. Citric acid is used again as a food acidulant in soft drinks. Then it is used in jams, jellies and candies. It is used as mordant in dyeing. If you remember, mordant in dyeing, those substances are used which are bifunctional. With the help of one functional group, they add on to the fiber, and with the help of another functional group, they attach to the dye molecules. Then magnesium citrate is used as an antacid. Antacids are the substances which are used as medicine to reduce the acidity in our stomach. So, magnesium citrate is one of the very common substances which is used for this purpose. Then its esters are used as plasticizers, and they are used in lacquers and varnishes. Then citric acid is also used for cleansing metals. Some articles made up of brass or copper, they get tarnished, and when they are treated with mild acid like citric acid, they get cleaned. Now, next we take up some unsaturated carboxylic acids. We have discussed earlier that carboxylic acids contain this R group here attached to the carboxyl functional group. Now, if R is some alkyl chain, then they are called aliphatic carboxylic acids. But if R is some unsaturated carbon chain, right, they are alkenyl groups, then we call these as a unsaturated carboxylic acids. So, basic functional group carboxyl group is same, and all the reactions of carboxyl groups will be observed. We will discuss especially the methods in which double bond is generated here and the reactions in which double bond group specifically undergoes some reactions. This is one example of unsaturated acid commonly called acrylic acid or propanoic acid. This is a 4 carbon unsaturated acid called crotonic acid or bute-2-enoic acid. In carboxylic acids, if there is a double bond, then obviously two geometries are possible. It may be cis isomer or it may be trans isomer. Here I have taken the example of a long chain acids which are basically fatty acids, because while discussing fatty acids, I will discuss this thing there, that how does it make some difference, the cis fatty acids and trans fatty acids in oils and fats. These unsaturated acids can be obtained by the oxidation of unsaturated aldehydes or ketones. Like this is an unsaturated aldehyde. This aldehyde group can be oxidized by mild oxidizing agents, and we will get unsaturated carboxylic acid. You see, the reagent to be used here should be such that which does not affect the double bond. So, we cannot use KMNO4 etc., because they will oxidize across the double bond also. We have to use mild oxidizing agents. Similarly, if we have an unsaturated ketone, this is an haloform reaction, treatment with NaOCl or NaOBr etc., and this part will be oxidized to carboxyl group, and here we will get corresponding haloform. Then we can get these unsaturated acids by the dehydration of beta hydroxy acids. We discussed that beta hydroxy acids on heating undergoes a dehydration of water molecule taking hydrogen from the alpha carbon. Dehydrohalogenation of beta halogeno-acids on treatment with alkali, they also eliminate a molecule of halogen acid taking hydrogen from the alpha carbon. Then there is a reaction called Nomenclature reaction, which involves the condensation of aldehydes with compounds with active methylene group like malonic ester, and here a double bond is created. Like this aldehyde is condensed with this malonic ester, we will get this unsaturated ester. This is hydrolyzed to give this dicarboxylic acid, and which on heating undergoes decarboxylation, and ultimately we get this alpha beta unsaturated carboxylic acid. The example of Nomenclature reaction, let us take this acetaldehyde, and it may be directly condensed even with malonic acid in presence of pyridine, we will get this unsaturated acid. It may be treated say with ethyl cyanoacetate, and this is acetone. A water molecule is lost, a double bond is created here, then this is hydrolyzed, this cyano group is hydrolyzed to carboxyl as well as this ester is hydrolyzed to carboxyl. We are getting the same malonic acid derivative here, and this on heating undergoes decarboxylation to ultimately give us this alpha beta unsaturated carboxylic acid. Then there is a special method for the preparation of acrylic acid, because acrylic acid derivatives are used in formation of some polymers also. This is acetylene. When it is treated with carbon monoxide and water in presence of nickel, we directly get this acrylic acid. Some properties of unsaturated acids. Reactions due to presence of double bond. Obviously, these reactions are electrophilic addition reaction, and as I told you, we will discuss this reaction to understand that why this addition occurs in such a way that negative part is going to the beta carbon and not to the alpha carbon. Like we discussed this reaction that alpha beta unsaturated acid, when addition of water is carried out, the OH goes to this carbon, whereas according to Markovnikov rule we accept it to forming the alpha hydroxy derivative, that we expect that this hydroxyl group will go at the alpha carbon. Similarly, addition of halogen acids, I discussed at that time that this bromine goes to this beta carbon and not to the alpha carbon here. So, in electrophilic addition, this is say HZ, any electrophile group which is going to add across this double bond, but there is another double bond here between carbon and oxygen. Now, normally in alkenes we find that this HZ is to be added across this double bond, but there is a now competitive reaction across this double bond also. And what happens, this group CO, this CO may be aldehyde, ketone or carboxylic acids. So, what I am discussing here, it is valid for unsaturated aldehyde as well as ketones also. This electron withdrawing nature of this carbonyl group withdraws the electron from this carbon-carbon double bond, and it deactivates this double bond for the electrophilic addition reaction, which are the very common reaction for simple alkenes. So, now what happens here, when H plus part of the group which is going to add approaches this molecule, there are two positions where it can go. It can go across this double bond or it can go across this double bond. When it goes across this CO double bond, H will obviously go to oxygen being more electronegative, and positive charge will go to carbon. And then this positively charge is stabilized by resonance with this double bond. So, this is a resonance stabilized carbocation which is formed. But if H plus goes to this carbon, then it may go here or it may go here. Positive charge, if it is here, this is an unstable carbocation because it is next to the electron withdrawing carbonyl group. If H goes here and positive charge is on the fourth carbon, that is fourth position, even that carbocation will not be very stable because it is not resonance stabilized. So, this reaction which is generally accepted for alkenes is not occurring here. Now, the H plus is going to CO double bond double bond part, which is shown with the blue color here. And once this carbocation is formed, then the negative part, now again there are two positions, it may go to this carbon or it may go to this carbon, because this carbocation is existing as a resonance hybrid. If it goes to this carbon, we will get a situation where carbon will have electron withdrawing groups, hydroxyl, another hydroxyl of the acid, and this Z, which is unstable. It goes here and we get this compound which is like an enol form. It undergoes ketonol tautomerism and H from oxygen shifts here. So, what we are getting as a final product? We find that in the final product, this HZ has added across the double bond of the alkene part, and carbonyl part of the acid or aldehyde or ketone, it has been obtained as such. But the negative part, that is the Z, has gone to this carbon and not to this carbon. So, this explains the mechanism for the addition of halogen acid or water, etc., across this double bond. Let us quickly take some examples. If it is addition of water, OH will go to this carbon. If it is addition of any alcohol, OR will go to this carbon. If it is addition of HBr, Br goes to this carbon. Maybe HCN, cyano will go to this carbon. Then any amine, again the amine part will go to this carbon, that is a beta carbon, and even with thiols, the SR part will go to beta carbon. So, this explains that why addition reaction across the unsaturated carboxylic acid, the negative part goes to the beta carbon. Then quickly let us take up some other oxidation reactions. The double bond may be oxidized by dilute KMnO4, we get corresponding dihydroxy derivative which may be further oxidized. Then this double bond may be reduced and we can get this saturated carboxylic acids. Then reactions due to carboxylic group, they show all the reactions, they react with sodium bicarbonate to form sodium salts, or alcohol to give esters, or they may react with phosphorus trichloride, pentachloride to give corresponding acid chloride, which on reaction with ammonia will give corresponding amides. So, this was about different substituted carboxylic acids. We have discussed briefly the methods of preparation and properties of halogen substituted carboxylic acids, hydroxy acids, and some unsaturated carboxylic acids. So, this was about different type of carboxylic acids. About the acid derivatives, which I said that OH group of the carboxyl group is substituted, that we will take up in a separate session later on. Thank you very much.
Right, thanks a lot sir for this very interesting presentation that we had with a number of visuals, also for clear illustration. So friends, just to inform you, this was our last lecture in our series of carboxylic acids, and there are 3 lectures which you could watch and very effectively form the connection. So with this, I thank sir for being here. Thank you so much, very kind of you to come here and spare your valuable time, and thank you friends for watching. Have a great day.